You want the AC running or Windows?
Just good. Like a little bit.
If it gets noisy, you All right, welcome back everyone. Hope you all had a restful weekend because we have a heavy week ahead. So heavy, I guess.
Not as heavy today, right?
Not as heavy. I think she's gonna make it.
Oh, she's gonna make it.
Yeah, I think
Okay.
she's gonna make it. So,
All right, so let's find out. So then all right. So I guess so we can finally prove this theorem. That if, real-algebraic Levi-flat hypersurface non-singular, then near each are local coordinates. The W M given I measuring the W equals 0. It's saying there are no bi-holomorphic invariants for real-algebraic manifolds. Now, for this, the best statement of being Levi-flat is the statement about the commutators of vector fields. So if x p 0 vector field we have that IP was the natural projection onto that direction. So basically, you're just sort of dropping everything that's in any of the 1, 0, 0, 1 direction. Right? Bar it's 0, it's a 0 vector. And I guess some of you that tried doing this, the exercise showed this really gives you the Levi form, right? I mean, like this thing goes into a vector space, not a, but it's a one-dimensional vector space. It's the Levi form, if you pick the right basis, right? But here, for Levi-flat, we don't have to worry about that because we don't care about anything being positive, negative. We just 0, and then it doesn't really matter what basis you pick, right? Now, from this, we want to show that that the T10 direct sum T01 is involutive. So there's I guess a couple of steps to it. So first, we don't just want this. We want that P 1 0 for x line sections, so all vector fields. Why is that true? That's true because if you have a Hermitian matrix, right? Knowing that the corresponding quadratic form is 0 is the same thing as the matrix being 0, right? So if you know, you basically can recover the matrix from just knowing the quadratic form. So there's maybe side note in linear algebra, right? I mean, if I know that, so this is just, A is Hermitian, right? And I know that this is true for all B, right? And the reason why I want to make a bigger deal out of this, because this is an example of complexification, right? I can think of the components of B as being variables, and I have my z's and the z bars, right? And the whole point is that, yeah, I can treat the z bars as separate variables, right? And so if I have, it's basically that theorem or lemma that we proved, right? Somewhere over there, right? It was that there's only the complexification is unique, right? Gives us that you're gonna get this thing for all EFW, right? I mean, just this is just a little bit of linear algebra, but it's this is actually what's being generalized for this, right? I mean, essentially, and you can there's a way of thinking about real analytic functions as basically being some sort of a generalization of this sort of thing, right? That you have it just instead of plugging in vectors, you're plugging in basically vectors of different monomials, right? Vectors of all possible monomials. So you can think of a real analytic function as an infinite by infinite matrix, right? And it is actually a nice, or it can be made into a nice operator. You have to worry about conversions and all that, but we don't have to worry too much about it. But it is actually, sometimes it is this, this statement, right? Okay, so that means, I mean, underneath here, the main bit is this Hermitian matrix being 0, right? So whether how do you do this, right? I mean, you do this. How do you compute the commutator? I mean, it seems like you need the whole vector field, right? But if so say if you remember, I don't know if all of you had some differential geometry or something, right? I mean, you start with 2 vectors and you extend them arbitrarily, and it doesn't matter how you extend them, right? It only to compute it, you need to extend, but it doesn't matter how. And so so in the end, it really just depends on the vectors, and it is just underneath. There's just a statement. This is just going to be a statement like this, and this is going to be exactly a statement like this, right? You start with a different vector, and you are barring everything. So it really is this sort of Hermitian statement over here. All right, so we have this, and so what do we do with it? So what does this thing say, right? It says, let's get rid of the pi. So it just says that this x1 bar b is it's actually a vector in the t 1 0 some t 0 1. Right? Because the projection to the remaining direction is 0, right? So it's here. So now, from that, we want to conclude that this thing is involutive. So it's not quite there yet, because if I take a random vector over here, it's not a vector here or a vector here. It's the sum of both of them. But the thing is that these guys themselves are involutive. Right? If I have x, so let's suppose it's still in, it's still a vector field in P1 0, right? So if I do, or let's suppose x and y, right? Just like over there, right? So if I do the commutator of x and y, well, what am I doing? Right? I have a vector that's written in the d by dz's and no bars, and another vector that's written in d by dz's and no bars. I don't even have to compute anything. I mean, there's no way that I'm going to get any d by dz bars out of it, right? So this is clearly in this is going to be a vector field in right, and similarly for the bars, which are like this, right? So this is going to be the T01. Right? For the same. So I have that these guys are involutive, and the Levi-flat condition says that that if I take something in here and I apply this, it's back in here. Well, I could also take something in 0, 1, right, and apply this, and still be in here, right? That would just be barring this thing. But if it's in here, if I bar anything, if I take the conjugate, the z bars become the z, but it still stays in here, right? So from this, I also get it for 0, 1, right? So if I take an arbitrary vector field in here, well, I can always write it as a vector field in here and a vector field in here. Then if I'm taking the commutators, right, the commutator is going to be a combination of commutators, right, just by linearity. You're going to have commutators coming from here, and then these kind of commutators, and then the bars of those, right? And in all of those, we know that you end up back in here, right? So that means, so all of these things mean that the commutator of electric field there is back in here, right? Now maybe it's good to sort of figure out to realize the difference between this being involutive and this being involutive, right? Because when you're first thinking about it, you might be saying, well, if I'm trying to sort of create holomorphic submanifolds, why isn't this being involutive enough, right? And yeah.
How are they individually?
Oh, these guys?
Yeah.
It's just because it's based on, so maybe let's suppose that you're in the first one. So what is what would x be, right? I mean, these are functions, right? Not necessarily holomorphic. Even though these guys might be called holomorphic vector fields, if we're on a CR manifold, they don't have holomorphic because it doesn't make sense. We're going to be on a hypersurface, so doesn't make the dimensions aren't. But it's something like this, and the same thing for y, right? So no matter how you compute the commutator, and there's just absolutely no way to get like these are the only things that are going to be in the commutator, right? There's going to be some combination of those.
Possible that this the bracket could be in T10 CM and not
No, because these all are tangent, right? So they are tangent vectors. Oh yeah. So now I see your question. Yeah, they are tangent vectors, right? I mean, we're just looking at a. I mean, they're in the complexified tangent vector, but yeah, I mean, if you take a commutator of tangent vectors, you get a tangent vector. Yeah. So, all right. So we have that this thing is involutive. Okay. Yeah. Maybe coming back to the comment that I was making before, right? So it might seem reasonable that why isn't this enough, right? But it shouldn't. Obviously, it shouldn't be enough because that would say that every CR manifold is Levi-flat, right? Which is clearly not true. That every that every hypersurface is going to be foliated by complex hypersurfaces. So the point is that we don't have that these are, these vector fields are not, they might be in the holomorphic derivatives, but they are not holomorphic vector fields, right? If I had actual honest holomorphic vector fields in CN, right, then I had, then they would be fine, right? But that's not what I have, right? I have a real tangent space, the TM, right? Maybe complexified. That's just adding in a little bit more algebra. But it's a real tangent space. It's a tangent space of a real object, and I have to look at the entire tangent space to see if something is involutive. And that's why I have to look at this whole thing and not just a half of it, right? Because we're not dealing with holomorphic things, right? That's the thing. So okay, so this is involutive. So apply Frobenius. Maybe I should. This is not the Frobenius that you were talking about, but it's almost there. It's almost there. So we want to apply the real-analytic Frobenius, right? In the real-analytic regularity. If this is involutive, so it's this. If I take just intersect, I mean, just do it, point-wise. So this guy is in the complexified tangent space. So just look at the part of it in the real tangent space. It's still going to be involutive. It's why? Well, if I take two vector fields in here, well, they're in here. So if I commute them, they're back in here. Well, but they were tangent vectors, so they were in here. If I commute them, they're back in here, right? So they're in both things. So this thing is involutive, right? So in some sense, we didn't have to do this, but if you want to apply the real-analytic Frobenius, it's really is talking about this thing. So apply real-analytic Frobenius. Real codimension 1 foliation M. Now we are only interested locally, right? So let's not worry right now about the whole foliation on M, but yeah, we do get the foliation everywhere, right? Now this is called this is the Levy foliation. So now we're at a point. So at near P, there is this, so that I don't get, I guess I just called it that.
We are taking intersection with TM or TPM?
Oh, TM. I mean, it could be with, either, I mean, I'm just thinking point-wise, right? If I'm doing this. Right.
Yeah, but
I mean, the intersection is point-wise or the whole thing. It doesn't really matter. I guess.
yeah, but point-wise, how do we get the liaison structure at a single tangent space? Like, what did it depend on the extension of the vector field you are taking?
Yeah, but the extension is always going to be, it's always going to be. I mean, because it doesn't, the commutators don't depend on the extension, right? Which extension you take. So you could take an extension. I mean, if you're starting with two vector fields in here, right? So two vectors at some point, you take an extension that's in here. That's still, I mean, basically you take an extension that's still tangent, right? Because you have two tangent vectors, so yeah, you can make you have two real tangent vectors, so you can extend them as real tangent vectors, right? Does that make sense? So all right, so we have this foliation. So near some P, there exists a subversion F. Maybe I'll write it as without loss of generality. You don't want to come up with a with a small neighborhood in M, you can come up with a new letter. So without loss of generality is defined in all M because you could. We're talking about small, so we could just take a neighborhood and say M is that neighborhood, right? The neighborhood in M. Just going in here, such that the level sets F are the leaves foliation. Right. So we have this is on M, right? You know, this is M, and we have these leaves, right? And these are the level sets T, right? These are the level sets of the level equation, right? So yeah, so F should be real-algebraic. Right, so I wanted to apply the real-algebraic Frobenius, so I should get it should be real-algebraic. I mean, you know, the Frobenius will provide you with lots and lots of these facts, right? It's by no means unique. And if you apply the smooth Frobenius, it will give you a smooth one, right? It might give you a smooth one that's not real-algebraic. It might give you C1 guy that's not real-algebraic. If you maybe you need at least C2, but C2 one that's not real-algebraic. So
I'm sorry I missed that, but what is the intersection of EM?
So we just need to look at the real, right? Because this is in the complexified, we need to look at it in the real time space. Right? Because we're applying the real-algebraic Frobenius. The way it's stated is for. I mean, you could come up with a statement of Frobenius for complexified tangent vectors, and it would essentially be exactly the same. It doesn't really matter. But if we're applying it, then you have to apply it to the space.
So you think of TM as the R copy sitting inside the complexified tangent.
No, I mean the TM is the standard tangent couple, right? Of M. Just the think of it as M is lying in R2M. Right? So before we complexify it.
So you kind of undo the complexification process and then ask for real coefficients.
Right. And the and of course this thing, maybe this was actually the other way of getting at the CR structure would be to actually look at this. This is this is sometimes the space that people are interested in. This is the space that's fixed by the complex structure by what Freud was calling J, right? So this is the J fixed guy, and the reason for going to the complexification. So maybe that's a good a good place to make a statement is the reason for going through complexification is that this thing does not split nicely. You can well, let's not do that, but you can think about, you can identify this space with either this or this. Not naturally, because you have a choice, but you can, this space can be, it's a real, at each point you get a real vector space, and it can be given not naturally, not naturally, but there's two choices, right? You have two choices. It can be given the complex structure of either this or this, right? But it cannot be split, right? You cannot write it as a direct sum of some natural object. To write it as a direct sum, you need to complexify, right? So this thing doesn't split. It only splits once you complexify, right? Okay.
And just one more question. So this is still involutive with the Levi-flat, the intersect with the TM.
It's
the intersection with the TM.
Right.
Is that still involutive?
Yeah. So if it's if this is, so start with two vectors, extend in the tangent space, then you know that they're back in here because that's involutive.
How they do the commutator and come back.
You know that they're tangent because So all right. Oh, so we have this submersion. So and importantly, the derivative is not zero, right? The submersion. And yeah, we asked for a real analytic one. So again, it's not at all unique. There's lots and lots of choices, but it is constant along these leads, right? So it is, there are level sets of the leads of the Levi foliation, which means that if X is a vector field in, let's say 0, 1, but it could be in either 0, 0, 1 or 1, 0 or in the direct sum. It doesn't really matter. Then you have that X has 0, right? In particular for these guys, but it's really for anything in any vector field in here, right? That's what the Frobenius term gives us. So F is not is real-algebraic CR, so it extends to a neighborhood. Now again, we don't have to. Oh, I guess we don't have to get a smaller neighborhood. But I guess what we proved was just in a neighborhood. So maybe think about it again. Maybe making a smaller neighborhood if you need. But you can actually, because the extension is unique, you have in a neighborhood of n. But f is in omega, so it extends as a holomorphic function to a neighborhood. And we only did locally, but yeah, again, you can, if you do it at each point, the extension is unique, but we don't really care. Make m small enough, right? Just take a local extension. That's fine. So without loss of generality, make m even smaller near some point. And you have this holomorphic function. Now, so suppose that I want over here, so I want some near some point, right? So at some point, I want to get these coordinates, right? So assume m and f of t is 0. So I'm gonna get I'm gonna get coordinates that vanish at t, right? Assume by translation, assume C1 Cn also I should that seems right. Yeah, maybe like an opposite statement, right? But thinking of them as holomorphic coordinates, right? So if I do a translation, think of these as holomorphic coordinates instead of coordinates on the underlying Cn, right? So after translation, I could say another way would be after translation, we can just assume that p is 0 if you want to say it that way. Now, the derivative of the df at d is not 0 because it's a submersion. It's not quite the right derivative. So maybe I should give this a name. So f. Right? So that I can also. Yeah.
Is now that W from your previous lecture, right?
That n is the little n.
I think he's saying you use the Z and W coordinates. So
Oh,
there's W here. Right?
Well, so these would be so if you wait for a little moment, you'll find out. So so right now there are coordinates on the whole thing, and I'm not going to use all of them basically. That's the thing. So it doesn't really matter, right? But you know, they might be. This might be. But it's not going to be that z. That z is going to be n minus one of them. But I'm going to use them. Right? They're going to be. I'm just going to throw one away. Right? Without also generality, I'm going to throw away Zn and not make Zn equal to W, but they're going to be a different W. Right?
How do we know that this F is defined on all of them? As in, Frobenius theorem only gives us.
So as I said, just locally. So that's what I'm saying without loss of generality, right? So you know, so make M smaller. We're only doing this locally, right? I mean, you're not going to get this globally anyway. I guess this doesn't work globally. Basically, for that, well, for a couple of reasons. First, the Frobenius is not going to work. You know, it's not going to give you this thing globally necessarily, and the change of variables is not going to work globally. So you can always, you know, you don't have to worry about trying to, like, if you worry about something not extending far, yeah, just take a smaller neighborhood, right? So over here, yes, same thing, right? Right. So yeah, I mean, you know, like over here, if you had a really large M, right? I mean, you could have this foliation that has dense leaves. I mean, that is entirely possible. Then you wouldn't have a global M, yeah, a global M. Right. All right. So if we have this, so there exists some J. Right, that I mean, f is a real function. So you know, the derivative not being zero, I mean, well, some partial derivative is not zero. But if some partial derivative is not zero, well, the same thing happens for the bar, right? So that means that either some z derivative or some z bar derivative can't be, you know, well, or and, right? I mean, we have to have both, right? So I can assume that there exists a J such that df dzj at p is not zero, right? That also generality J is n, right? And what does that mean? I mean, this is just a restriction of capital F to M, it's nearby. So so that means that N is not there, right? So what I can do is I can change coordinates. Yeah. So this is basically just change the order of the z1s through zn, right? And so now take coordinates one through zn minus one, and for this thing I'm going to use capital F. Right? So I'm going to use capital F. This is my so maybe let me go to W, but W is capital F, right? Capital F, you know, I guess it originally depends on all the z1s through zn, right? But this is a local change of coordinates, right? Am I doing the right thing? Yes, I think so. So and so here, well, what was M? It was really where F was real, right? So M is defined in P by imaginary capital F being zero or imaginary W being zero, right? So it's it doesn't really matter, right? Which one? Yeah, you can really the main thing is just to get this thing. Now, why is n exactly that? Well, I mean, it has to be capital F. The derivative of capital F is non-zero, so therefore this is giving me a hypersurface. Right? That hypersurface contains M near P. Right? I'm not going to be able to have any other. Gonna have any other pieces. Right? If it was singular, then maybe, but if it's a non-singular, you can't fit a little piece of the same dimensional manifold inside another manifold without taking up the whole neighborhood, right? The only open submanifold at P is itself, right? So it has to be equal. Yeah.
This thing, what does df by dz mean? Like as in small f. F is on M, right?
Yep.
And
I guess I should right. This made sense yesterday. Now it doesn't make sense. Right. I mean, you're gonna have. I guess we should. Maybe this was not the. Well, I guess the remaining statement makes sense. It made sense yesterday. Yeah, it's little f is on M. So, but it's still it's going to be. So if you think about it as well, I mean, it has to be. So maybe say it this way.
Why does it not make sense? Because
it's not maybe tangent to. I mean, you could I guess make it tangent. You can make it tangent, but by some rotation. But I don't maybe don't want to do that.
What is not tangent?
The d by d Cj, right?
No, but you see when we are taking M smaller, and we are
yeah, but it's not gonna like.
But
this is a holomorphic vector field. I mean, it might a holomorphic vector. I mean, it might not be tangent. Yeah.
Oh, you mean like on the leaf?
Right.
Well,
I mean, it's
on the manifold.
on the not tangent to the manifold.
Why not?
Or it doesn't have to be.
So where are the coordinates? I thought you were taking the local chart for that.
I see.
Yeah, but it's like this is the d by dZj is the that's in Cn. So that doesn't necessarily have to be that. Those guys don't have to be that. So maybe so maybe think of think of it this way. So is this so it's so that means so let's do it this way. So I don't have to okay, so this is not zero, so the f p is not zero. So assume this regardless of generality that let's do this way that's the holomorphic gradient over here this as a vector is linearly I'm saying the same thing. It's always I mean, so assume you could assume that this is not zero. So, okay. Just don't do it with little f, right? Okay. Now it's just not zero, right? Okay. Maybe I did that one. Anyway, maybe that's why it makes sense. All right. So that's it, right? So we have local coordinates again. They're just local, right? Globally trying to figure out a Levi-flat. I mean, that's the tricky bit. And we'll get into about singular Levi-flats. I mean, one way to think about singular Levi-flats. I mean, it's basically going to be a smooth Levi-flat that just, at some point it's not a smooth manifold. So if you ignore what happens at the singularity, you have some global Levi-flat, but now it's sort of somehow going around some point, and you want to figure out what happens locally. It's almost like global questions as well, right? So global questions about Levi-flat manifolds are difficult, and so it's singular Levi-flats are basically going to be like special global statements about Levi-flats, right? So there's nothing, nothing like this globally that you can somehow have a normal form globally. This was just it is too much. And maybe there's a way of doing it. There's some sort of normalization in small dimensions, maybe, but I don't think anybody's anybody's done this. So because in some sense, in small dimensions, it should be fairly simple. So I guess I can give you a total classification of Levi-flat manifolds in, let's say that the one-dimensional project is in the sphere, right? So if you have closed Levi-flat, well, it is a circle, right? It can be changed into a circle. So it's CR diffeomorphic to the circle. But that's it, because in C, Levi-flats are just real curves, right? But yeah, in higher dimensions, things are difficult. And actually, I want to do later on. I don't know if I'm going to get too far into it, but I want to do one. This is sort of fairly so it's important conjecture which is still not answered, which is the non-existence of Levi-flats in Pn, and you think that it's that it's answered if you look at the literature, because for example for n equals 2 there are two papers, at least two papers, or two papers that I know of, that answer it in P2, but they're both wrong. So one of them is in the annals. So like if there's a paper in the annals, right, it's got to be answered, right? But it's not true. So in n equals 3 or higher, we know that there is no smooth closed Levi-flat hypersurfaces in Pn. In P1, I just gave you an example of the circle, right? So P1, yeah, those lots, but P2, nobody knows, even in the real analytic case. Okay, even though locally we have really nice things, and actually we get more out of this.
The conjecture is there won't be any Levi-flat surface on Pn.
Yeah, the conjecture is that there isn't one. But at this point, it's like I'll go through the proof, given lots of black boxes on this, but it's so it seems to suggest that 2 is special, but it's unclear. It might be just that this technique fits, right? But so it's unclear. I think most people think that there isn't one, right? But whether there is or isn't, right? There's been lots of conjectures that turn out to be wrong, right? All right.
So what can I say about the smooth analog of these patterns there? There is some kind of smooth analog.
So I guess what you could do as a smooth analog would be, you get basically here, right? So you get a CR smooth function that is giving you this foliation, right? But a smooth function is not necessarily going to extend to anywhere. So you're not going to get holomorphic coordinates that give you this, right? But you could there's a CR diffeomorphism, right? Because you're getting like on the manifold, you have so you can you could come up with coordinates where you have nice coordinates in the z's, but then the w coordinate just doesn't, right? So if you're thinking intrinsically in terms of just it's a smooth thing, so you can only do smooth things. You maybe intrinsically can't tell the difference, but but you cannot make holomorphic change of coordinates in the ambient space to make it this, right? So in some sense, smooth ones are also not too bad, right? I mean, you're getting quite a bit, at least sort of as far as the CR geometry intrinsically is concerned. They are basically kind of the same, but you just if you're thinking of these guys being somewhere existing in some ambient space, then you don't know, right?
So, level curves will be still complex manifolds?
You will get that the level curves are going to use complex manifolds, but they're not put together nice. So yeah. Yeah, I mean they're somehow you can't by holomorphism you wouldn't be able to straighten all of them. Like you could straighten one, but you don't know what to do with the others, and you don't know if if you can straighten the others or even try to put them in the. So yeah, it's you can do it smoothly, right? But if you're doing smoothly, you lose the it's not a biholomorphic change of coordinates, right? It's a CR diffeomorphic change of coordinates. So I guess as a CR manifold, if you don't want to do it biholomorphically, then this is true, right? That you can go that it's CR diffeomorphic. That means that there's a smooth CR diffeomorphism that goes that makes this guy equivalent to the smooth Levi-flat. But yes.
But when you get the normal form, we'll have like an O2 term or O3 term.
In holomorphic coordinates, yes.
In the the smooth.
Yeah. In the smooth, but that's if in the ambient coordinates. Sure. So if you're allowed to make CR diffeomorphisms, right, you're not necessarily getting biholomorphisms. That's the thing. So you can get rid of more stuff by a CR diffeomorphism, but it's it depends on what you want, right? I guess.
Yes, so how far can you go with biholomorphic coordinate changes? How far can you go to biholomorphic coordinate changes? So maybe there will be some other.
I'm not sure where what would be the first obstruction. I didn't really think about this ever. There was there were some papers on trying to normalize smooth Levi-flat, but I don't know. So I don't know if I mean surely you can do the Chern-Moser theory and try to zero out as many terms as you want. I'm not sure where you will what's the first place that you hit. I'm not sure. I've never I mean wait, Chern-Moser they're all zero. That's formally they're all of these things at the point are zero because for the same reason, right? I mean it's so it's going to be more complicated. I mean you can only do it formally at a point, right? Yeah. I mean it's basically this because if you can do this you can do it formally, right? So there shouldn't be hopefully I'm not saying something stupid at this point, but I think that should say that there are no at the point you right. So you will get you'll get I guess there's going to be a formal normalization. I assume this should mean that there's a formal normalization that you make this, but then it's not going to be convergent. Yeah.
So the trivial bound will be O3, but without additional hypothesis, we should be able to write down examples where that is actually realized, right?
For the O3, it's easier. Like we've already done that, right? Yeah. So so we should be able to So we should be able to
more structure on the manifold to be able to say something more.
So hopefully I'm not saying something really stupid at this point. but I think, unless I'm having a think of, is you should be able to basically have OK for any k, right? By holomorphically, but not identically zero. Up to arbitrary order, basically. I think, unless I'm, unless I'm getting something confused in my head. But I'm also interested in real analytics, so I've never really thought too much about that.
Here, I have one question. Like,
Sure.
how do you know that like M is the only place where the imaginary part of it is zero?
So, because so if you the derivative of capital F is non-zero.
Yeah.
So this gives you locally near P, and we're only interested in near P. This gives you a hypersurface, right? So it gives you a 2n-1 dimensional real hypersurface, and that contains your F,
Yeah.
which is a 2n-1 real hypersurface. So it's going to be locally, it's going to be an open submanifold. So you're getting, they have to agree on the neighborhood. You cannot fit locally, same dimensional submanifold into another submanifold. That makes sense?
So it might happen that that is disconnected. So we just take the component which
Right. I mean, if M is if M is disconnected, I mean, this is all, but this is only local anyway. Right?
Yeah, that's
But yeah, I mean, you might get maybe you get that M does this, right, and then you do change your coordinates, and the F is only picking up this part. Yeah, I'm responsible, right? But locally, there's going to be some neighborhood where they agree. Right?
or it can happen that itself, the image F, the imaginary part of F equals 0, that itself is disconnected.
But again, I'm only saying here.
Yeah.
So yeah, I mean, if it depends on, if we're talking about this local change of coordinates, saying in a small enough neighborhood, right?
Are you also using F is real analytic at that point?
So capital F is actually holomorphic, right? Because it's the holomorphic extension of little f, which is real-algebraic. Right?
The smallest is reduced capital F in M.
So little f is on M, and capital F is actually in a neighborhood.
Yes, so they will agree on the neighborhood of P.
Oh yeah. So it's the extension.
Yes, so
So-
I mean, it's not only imaginary of F is 0, it's F is 0. Because small f of P is 0, 1,
It's but little f is not zero on, right? I mean, little f is real,
yes, so it is 0 on M, and for a point P on M.
right?
Right. And you are saying that capital F is
But just at one point, right?
yes. I mean, it's you are taking a particular point here.
Yeah, it's a particular point. Yeah. So near that point, I'm defining these change coordinates, right? So fixing the point P, and I'm just going to assume that f is 0 there, right? And then I'm going to translate so basically these guys are 0 there as well. Does that make sense?
Just have one question.
Sure.
This Levi form is preserved under the CR max.
So
The Levi form
yeah,
preserved under CR max.
I mean, preserved in the sense
Not in
that
the neighborhood of the manifold, but I'm just.
well, because the Levi form is intrinsic, right? I mean, it's that's basically writing it like this, right? I mean, it's writing it intrinsically, right? So yeah, that's going to be preserved. Well, preserved up to star congruence, right? So the same as you would preserve under biholomorphisms, but even then, right, it's sort of it's always dependent on the basis, right? So yeah, up to a change of basis, basically. All right, so we get something more out of this thing. So maybe let's keep the term up. But we get, and that we definitely don't get for smooth or nothing like it. So here, let's suppose that we have suppose here. P f is given by imaginary of w equals 0. So now I could think about it as well, it is giving me a foliation on a neighborhood in Cn. It's giving me actual holomorphic foliation, and I can get it by a number of different ways. I could get it as a one form. I could think of it as F is a submersion, right? Or W is a submersion. So W is a submersion. Etc. But I get we get holomorphic foliation on a neighborhood that agrees with the Levi foliation. What do we mean by agrees? I mean, in this case, it's even given by the same function, just restricted to m. But it has the same leaves, right? The leaves of basically the leaves of what are the leaves of this foliation? The leaves are where w is constant, right? Well, those are precisely the leaves. I mean, this is w, right? So it's precisely the same leaves, right? It's usually what we mean by we're extending the foliation, right? Two foliations are the same; they have the same leaves, right? So it extends. We get an actual holomorphic foliation in a neighborhood, right? So that's what we wouldn't get with smooth, right? Because there's no good way of extending it. I mean, I guess you could smoothly extend it somehow. Then you get some smooth foliation. But that would be it. And probably if you randomly extend it, that foliation wouldn't even get analytic. The leaves wouldn't be complex manifolds. They would just be some random manifolds of the same dimension. But you just get some smooth foliation. So that's not very useful, right? But here we're actually getting holomorphic foliation. And actually, this is one of the reasons why Levi-flats come up in holomorphic foliation theory, because they're the so for foliation, if something's called an invariant set, basically it's a union of leaves of the foliation. But that means that over here we're getting the Levi-flat. If we extend the foliation, then this is an invariant set, right? That it's composed of the leaves of the foliation. Basically, you just to get the Levi-flat, you just pick certain leaves, right? And you pick the leaves so that you get, of course, a real-algebraic manifold here. So it is possible to have like this is sometimes could be possible for a smooth function, right? I mean, it could be that you have a smooth manifold, smooth Levi-flat, where the foliation extends. You're just not guaranteed that that's going to happen. So if you pick you could pick a certain set of leaves that give you smooth manifold, but in general, that's not going to happen. So it only happens for real-algebraic. You're only guaranteed that for real-algebraic manifold. So we have a holomorphic foliation like this, and the thing is that the foliation is unique. You cannot. It doesn't extend in two different ways. Once you have the foliation, it's basically, I guess, you think about it as if I have. But think about it as one form, right? Suppose that you had another foliation, or of foliation that's given maybe as a one form omega, right? Well, what is that foliation really giving you? So it's giving you so if another one form omega holomorphic giving a foliation, so integrable, right? So d omega, which omega is 0, so giving foliation. With the Levi foliation M, then what's happening? You have that omega. I mean, the way that you can think about it, I mean, it's as Zoe talked about one-dimensional foliations. Two-dimensional one foliations are very similar, right? I mean, you're either talking about vector fields or one form, integrating vector fields, or you're integrating one form. You can think of the one form as basically giving you the normals, right? And so, how could this happen? It would be that you have that omega and dw are basically giving you their on M, they have to give you the same normals, maybe not the same size, right? Or same, they are two multiple by a complex number, right? But if you're going to have two holomorphic one forms that are going to there are going to be, I guess, the different functions are quotients of each other, then they're going to be the same thing. Another way that you could think about it is that so this is one of the coordinates. You could divide so omega, because it has to point in the same thing. So if maybe I'll write it down. It's easy stating it, right? So if omega is well, at first, I mean, something like this. Sorry, I'm writing out a vector field. Should be writing out. So I have the j, and then I have maybe omega and dw, right? But it has to point in the same direction. How could it point in the same direction? These are 0, right? So these are not there, and what I'm getting is just a holomorphic function times dw on M, right? So it is on M. But that means that's going to be true everywhere, right? Because I'm whenever you have this comes back to a question that somebody had done. No, you didn't have that, but somebody had that question long time ago about generic manifold, right? So generic manifolds are precisely the thing. If you have some sort of a holomorphic condition, something is 0, or some equation is true on a generic manifold, then it's true in a neighborhood. And a hypersurface is a generic manifold. Once you get some sort of a holomorphic condition on a manifold, or on a real hypersurface, it's true everywhere, right? So you will get this thing. I mean, these guys are 0 on M, right? There's no way that you can have a holomorphic function that's 0 on M and not 0 in the neighborhood, right? So that means that first we have omega j is 0 on M. So omega j, or well, I guess j is 1 to n minus 1, right? Not the last one, of course. So these are 0 on the neighborhood. So that means that we have a unique. So it extends uniquely, right?
It's your question. Well, like you say, is the can the possible like two different capital F?
Right. I mean, you can think about it as right. I mean, they have to, how they're related, right? Yeah, basically multiples of.
Since they are coinciding on hypersurface, real hypersurface, they just
Right, but they don't completely have to coincide, right? They could have slightly different values, but they have to. I guess they have to be, once you put it into this form, right? I mean, they cannot depend on the other variables, right? But they could still be, slightly different. Basically they're going to be functions of W, right? The functions of W that don't depend on. Yeah, I mean, you could get at this from. So this is looking at it from the one form point of view, and you could get at it from. Suppose that you have two submersions. Any one, or suppose that you have these two, two flattenings, right? Any one of these things, you could use. But again, it's sort of, I guess, they'll mostly talk about the one-dimensional, but it's, all of these things are basically just, or not all of these, but a lot of these arguments are very similar for the one forms. And so studying dimension one and studying dimension one are very similar. They're kind of dual to each other.
So when I go from this local form to the foliation, so
Yep.
the foliation there, let's say this foliation is very global.
Yeah, so you'll get, so basically because of this, you get global extension. So you get the, yeah. So this means, maybe I should write it down, right? This means that actually now we get a global result.
Since the local computations of the leaves may not be nice, the global use, right? Nice in the sense they might not be converted.
Yeah. So yeah, you could have, right? I mean, there's it's can give you a Levi-flat. So in I guess it would be C2, sorry, minus 0. You could have first of all I have Z and W. So there's this example. I think it was by Webster or Bedford, one of these guys. I can't remember now. And alpha, right? It's not a nice, of course, not a nice manifold at 0, but everywhere else you get a nice manifold, and you can check that the leaves are not embedded; they sort of go around in a crazy way. And so this would give you a Levi-flat in here, but you would still get a foliation in a neighborhood, right? I mean, you have to sort of think about it. Okay, it's going to be some sort of a. There's a really fake picture, right? But it would look sort of like this, and just sort of rotate around itself. But you would get a foliation in the neighborhood. You couldn't get a foliation in the neighborhood of 0, right? So the neighborhood where the foliation would happen is something like this, right? So you could extend it to a foliation in some neighborhood of this, not this, right? So because if you could, so can anybody say why I can't extend to? Maybe it's not so easy, but you shouldn't be extended. It's if I'm, right? As a holomorphic foliation, it shouldn't work. It shouldn't work because you would get actually a singular holomorphic foliation in here, but maybe it's not so quick to check that this thing. If I remember right, yeah, there is no singular holomorphic foliation. So
we cannot reduce the vector field.
No. Anyway, yeah. So maybe it's not so easy. Maybe it could be, an interesting interesting exercise that might or might not be hard. I can't think right now enough to say if it is or isn't hard.
Algorithm function will not be extended.
Yeah, something like that. I mean, that should be the, but I can't think right now enough to say that it is going to be a trivial computation or not.
Actually, it's some sort of linear vector. If you write x del by del, z del by del z plus alpha w del by w, something like that. The leaves of this vector will be something which we have like that. And then the closure of every is something.
Right. Hey, I mean, we can sort of, like this is a good thing for the discussion, right? So maybe we should, we have some nice discussion topic. So, all right. So basically, what this says is that we have this is true for any n. So if globally it's Levi-flat is Levi-flat C omega, and there exists a holomorphic foliation in a neighborhood, and such that M is an invariant that, or in other words, if the leaves of the Levy foliation are the leaves of this holomorphic foliation, right? So with this, we can actually give this, maybe good place to give a sort of a list of different conditions of being Levi-flat. Right? First, suppose M is let's suppose smooth first, right? Smooth real-algebraic, but we're just only gonna do it up to smooth. So smooth. So again, P is so T hypersurface. Then M is Levi-flat. And for a smooth one, you could have something that's Levi-flat and then supposed to be Levi-flat later on, right? For a real-algebraic one, don't worry too much about it, but you can, as long as it's connected, you could, as long as it's going to be Levi-flat just by the identity term, because the Levy form is going to be a real-algebraic function. So real-algebraic function still get identity term. So near P, if and only if one, so the standard one, the Levy form is 0. So that means that x, I guess I'm fixing P as a x at q. Let me just write this down. We've had a definition of this, so let me rewrite the definition. It's 0 for all q near P, and x being vector fields, or well, I guess in this case I just need vectors 1, 0, q, right? So that's just the standard definition. Q, we could I was going to give them in some order, right? The we could have this thing was imaginary W is 03, right? We did that. That sort of followed from this after some calculation. So there exists holomorphic coordinates W vanishing E with M E is given by imaginary W is 3. Right? We have this. Then we had maybe the absolute first definition that we did. That was with the disks, right? So I'll just, because it's not that important, I'll just give it in words instead of writing down the definition of the disks again, right? So I'll just say M is both sides. And actually, maybe we could, if you say this way, this includes a whole lot of different definitions, because there's a whole lot of different definitions of pseudoconvex. Any one of them that you take, as long as it's pseudoconvex on both sides, that's what it means to be Levi-flat. So you could do it in terms of the disks, and if you have a sequence of disks whose boundaries stay on one side of M, then the insides are going to also stay in the one side of M in the limit, right? You can do it from both sides, or any other definition of Levi-flat. As of pseudoconvex, but both sides are supposed to be pseudoconvex, right? So technically, that condition should have been holomorphically convex, but it's equivalent to pseudoconvex. All right, so that's for oh, right. Before. So then we have, I guess, this definition. From X in well, vector fields, 1-0 vector fields on N, right? Which we sort of saw in this, or at least in the discussion, maybe computed that that's the same thing as this thing, and all Q near P, right? If this, as we saw in the beginning, this is equivalent to cumulative right? So then you can apply for video. So we have a whole bunch of different. So none of these are really worry about real elasticity, but for if maybe I'll go here, but for real analytic, we have more. So if M is analytic and like that, then Levi-flat if and only if. Now we could we thought that first maybe we can actually just make that equal 0 if there exists holomorphic coordinates in W vanishing near P, there's M near P given by W equals 0, right? We could also ask that there exists holomorphic codimension 1 foliation near P, near P, M is an invariant set. Let's say F, right? So we have a whole bunch of different ways of seeing the same thing. And of course, this is so we're getting, I guess, from this, I guess that there, you could maybe I could put if I want another one somewhere between this and this, because we can just apply the provenience. So another way to say there exists a real analytic codimension, or now a real codimension one, foliation M with and I guess near P. It's complex C. Right? Because those complexities are automatically going to give you that their tangent space will have to be this by dimension, right? So their tangent space, their complexified tangent space is of this dimension, and has to be a subset of the tangent space of the of the manifold. So those tangent spaces have to equal, right? So it would be, if you want something in between. So how far can we get for smooth? And you could use that as a definition, but then for real analytic, you can actually extend the foliation to a neighbor. So here, real. I meant to say real foliation, real, but not analytic, right? It doesn't even make sense to say I have a smooth manifold. What does it mean to have a real analytic foliation? Real smooth. Sorry about that. Right. And I guess in my head I had the real thing, right? And I have a real codimension 1 foliation, right? Okay. I think I don't think I should try to go anywhere else. But so next time we'll do this proof of Lindsay, or at least maybe not do the proofs completely, but do the proofs up to a whole bunch of black boxes because they're just to see the idea of how it works and sort of see the main sort of obstruction for there to be smooth Levi-flats in PM or real analytic, but non-singular ones, and that sort of gives some motivation also for why I study singular, right? Because you're naturally going to get some singularities, and so if you're studying, so even if you're studying foliations, one of the things that people study is the invariant sets, right? So the invariant sets will invariantly have invariably have singularities, right? And so of course the singularities could be really really bad. So we'll focus on fairly nice singularities. That if these things are actually real subvarieties, which is a fairly nice type of a singularity. You could have much worse. I mean, it always depends on what do you mean by taking manifolds and trying to go into a singular setting, right? So maybe just there's a really nice term of Whitney, and so for real subvarieties, there's a zero sets of real analytic functions. For smooth, there's no good definition, because if you say, well, how about zero sets of smooth functions? So, well, if you have the derivative is non-zero, okay, so you get, let's suppose it's real value, you get manifolds. But if you don't assume that the derivative is non-zero, there's a term by Whitney that says take any closed set in Rn, absolutely any, no matter how weird, whatever Hausdorff dimension fractal nonsense you get, any closed set. So clearly there's a continuous function that's equal, but Whitney says there is a smooth function. So there's a smooth function whose zero set is exactly that set, and actually he gives more. There's a smooth function which is real analytic outside of the set, and it's only valued between 0 and 1. I mean, it is just so if you're talking about zero sets of smooth functions, yeah, you can't say anything. It's basically the same thing as zero sets of continuous functions. The same thing as just all closed sets, and so that's way too much, right? So if you're going to take sort of trying to generalize singularities from real analytic subvarieties is difficult, because you have to always put some conditions, because just saying zero sets of a smooth function, anything is a zero set of a smooth function. So I mean, it has to be closed, right? Because the smooth function is continuous. But yeah, other than that, you can't say anything. So all right. So let's break for it.